So Ben, can you start sharing? Yeah, thanks a lot. Very good.
All right, great. Can you hear me and see the slides?
Yes, absolutely.
Yes. Fantastic. Okay, thanks so much. So yeah, as I said in during the questions from the last talk, this will be sort of a complementary approach to what Stefano talked about, and it's sort of applicable in a model-independent way. So today I'm going to talk about two things. One is positive reweighting, and I'll explain in a bit why the positive is in the quotation marks. But the setting, which I think you probably all know, is that at some phase space point, there is a non-trivial distribution of weights. And that's what we want to try to work with. And that could be, a set of positive and negative weights, but in general, it's just any distribution of weights for a given phase space point. And the second part of the talk will be about neural reweighting. So in particular, X here, the phase space, is continuous and or high dimensional. And in that case, neural networks are very powerful as function approximators. Okay, so let me walk you through the idea. So suppose we have sort of the usual setup where you have some expectation value of an observable. And O here, script O, is going to be the observable. And if we want to compute the average value, it's just a sum over all the events xi, all the events I, and we have O of xi is the observable, and they're weighted by their weight wi. And this is basically this is generic. So this is true for any observable we want to compute anywhere, basically. And in particular, it could be like the content of a histogram bin, where O is just 1 if it's in the bin and 0 otherwise. And in what I'm going to show here, although it doesn't matter too much, the weights are going to be normalized to 1. So in the unweighted case, wi is just 1 over n. Okay, so the really important thing, which is the basis for all that I'm going to talk about today, is that you can reorganize this sum to write it like this, where you sum over all the unique values of the observable. And then for all the unique values of the observable, you can sum over the weights for all the events that have that value of the observable. And if you write the sum like this, where inside the inner bracket, you basically summing over all the n sub O events that have the same value of the observable, you can see that basically we're only sensitive to the average weight. So that quantity in parentheses there is basically the average weight. And so the observable, which is all that we're sensitive to, we don't care about the distribution of weights. We only care about that sum there, which is equivalent to the average. Okay, so that's going to be the basis of positive reweighting. And in particular, let me tell you a bit about what the idea is for this approach. So if there's no information in the distribution of weights, P of weights given the observable, except the average, that says that we can simply replace all of the weights in our ensemble of events with the average. And that's illustrated here, where you can imagine you have this set of events where you have, 3 events. They all have the same value of the observable O. They have 3 different weights. We're not sensitive to the distribution of weights. Physically, that's not meaningful. And so we can just replace each of the WIs with the average of the 3. So that's observation number 1. And the second observation is that, in fact, you can replace all events with the same value of the observable with some representative events, say k events, that all have that same value, and a weight, which is k times the average. And so in this particular case, imagine you could set k equals 1. You see that the same event is basically repeated 3 times. It's identical. And so you can say, okay, well, I'll simply replace these 3 events with one event, one representative event, where the value of the observable is the same, and the weight of that event is the average weight times 3. And you can see that if you compute expectation values of this observable, you get the same answer whether you use the top left, the top right, or the bottom right. They all have the same weighted average. Okay, and why is this useful? Well, this is useful. So it doesn't actually save you on the event generator level. So you still need to generate the original events to do the reweighting. But this can be very helpful if k is much less than the number of events that you started with the given value of the observable. You can pass far fewer events through the detector simulation. So that's where the gains can come from. And so in this case, you'd have a savings of 3, factor of 3. You would simulate only one event instead of simulating 3 events. Okay. So that's the idea of this resampling. But we don't just care about cases where the phase space is discrete. So what if the phase space is continuous? And you can apply basically the same methodology in that case. So you can imagine discretizing your phase space with very, very small patches. You look at a particular patch of the observable, where the observable is, let's say, relatively constant. And then within that patch, just as before, you're only sensitive to the average weight and not the distribution of weights. And so we can play basically a very similar game where this bottom equation here is just reorganizing like I did before, where we sum over, we have the top is where we sum over the weights, and then the bottom we can, we show that you're only, it shows that you're only sensitive to the average. So it's just some manipulation where you can sum over the weights in a given particular patch of the phase space. And then you can, for instance, let's say you replace K, you used K representative events. And then you see you get this value of K times the average value in that patch. And so let's imagine that we have a new weight, which is K times this average value W, and that's like the W new in the patch. And so this is exactly the same as the discrete case, where now we sum over N over K events instead of the original N. But it's exactly the same as before, but now we can ask the question, what is a good value of K? And so in principle, any value of K is fine from the point of view of preserving the cross-section. So whatever K you use, and even if you want to use K equals 1, you preserve the cross-section, but not all values of K are equally good. In particular, what we would advocate is that the best value of K is one that preserves not only the central value, which is true for all values, but also the uncertainty. And so in particular, imagine this patch that we're talking about, you want to match the sum of the squares of the weights, which would allow you to locally preserve the uncertainty. And so in particular, if we have this new weight that I talked about before, which is K times the average weight in the patch, then if you take the sum of the squares of the weights in this patch on the left, we want it to be equal to the sum of the squares of the weights before doing any reweighting. And you can take this equation and you can do some simple manipulation, and you can show that the squared weight in the patch should be about K times the average value of the weight squared, which is just very simple arithmetic to do that. And then that gives us sort of two equations, which is what you might expect. We have two equations which set the cross section to get the cross section right. That's the first one, and then the second one gets the sum of the square of the weights right, and that basically tells us what K should be. In particular, this says that the optimal value of K on this patch is the average value of the weight squared divided by the average value of the weight squared, where those pauses are important to denote when the squaring is happening. And I'm here talking about patches, but we want to take the continuum limit. And if you take the continuum limit where the size of the patch goes to 0, then you have basically a function K. And this function K is a function of the phase space, where locally you want this resampling factor to be the expected value of the weight squared divided by the expected value of the weight squared. And in this case, I'm going to use uppercase here denotes random variables. And if you want to see the technical details with all of the equations properly accounted for, it's in detail in the paper. Okay. So this gives us a very natural procedure for applying this resampling, local resampling, and preserving the uncertainties. So there's sort of 5 steps. First is you estimate the average value of the weight. Then you estimate the average value of the weight squared locally. These are local functions now. So for a given phase space point, you know the average values. Then in step 3, you define this reweighting factor, this local reweighting factor, as the ratio of these two averages. And then you can apply the resampling. So for each event, you basically reject it with some probability that's given by K. And And then for the last step, you take the local weight and you scale it by k in order to account for the ones you've thrown away. And if you do this procedure, we claim that the cross-section is preserved and the uncertainties, local uncertainties, are also preserved. But this very naturally then leads me to the second part of my talk, where we can ask the question, how do we estimate these local expectation values? And that's where neural resampling comes in. So in particular, it's based on two facts. Fact number one is that neural networks are great function approximators, especially in high dimensions. And the second fact is that neural networks trained to distinguish two samples learn to approximate the likelihood ratio, or rather something that's monotonically related to the likelihood ratio. And in this case, we basically want to learn an unbinned likelihood ratio to distinguish between a weighted sample and an unweighted one. And unfortunately, I don't have time to go into the machine learning details, but I'm very happy to discuss it if you're interested later. But the very high level version of it is that you can use a very simple loss function. And so basically here, G is a neural network, which is a function of the phase space X. And the idea is to train this is a classifier. So it's using the binary cross entropy, which is one of the most standard loss functions. And they're sort of the first, in a typical classification task, you'd have like one term for the signal and one term for the background. Here there's no signal and background. We're distinguishing one sample from itself where one of the times it's weighted. So in the first term here, this is the weighted sample, and the second term is the sample unweighted. And one can show that if you train a classifier in this way, that asymptotically you get this nice relation where this particular combination of the function with itself gives you the expected value of W given X. And so in this way, we can learn the local weight, the local average weight as a function of X. And the same story goes through if you want to learn the weight squared. In the examples I'm going to show below, all the weights are plus or minus 1. And so in that case, the average value of the weight squared is no different. But because the weights are all, the W squared is equal to the average value of W. But you in principle can apply this same procedure if the distribution of weights is non-trivial, not just two values that are plus or minus. Okay, so now let me show you how this works in action. And so as a first example, consider a simple case where you have a Gaussian. And in order to make it interesting, let's imagine you have a Gaussian, a superposition of a Gaussian and a negative Gaussian. And so if you do that, you get this carved out looking double hump structure on the left. And you see there's three histograms. One is the one with initial weighted distribution. Then you have two versions of the neural resampler, one with the optimal K and one with K equals 1. And as advertised, it doesn't matter what value of K you use, you get the cross-section is correct. So the sum of the weights, locally here is correct. And I'll say something more about the uncertainties in the next slide. But I wanted to show here the distribution of weights on the right. And so the blue histograms show the initial weight. So they're all plus or minus 1, like I mentioned, where we have slightly more positive weights. So the distribution is, totally the cross-section is positive. And then you can see the weight distributions. And what's nice about the Gaussian case is that we can actually derive analytically what the weights are. And so we can compare our neural network to the values of the analytic weights, and we see that they're the same. So it's hard to see on this plot, but basically behind the histograms, there are also lines, and they're exactly the same. And the distribution for the optimal K has a broader weight spread because it has to account for the events you've thrown away, which we'll see in a second. But the last thing I wanted to comment about the plot on the left in particular is that it's binned here, but the binning is only for illustration. The resampling here is actually unbinned. So you could rebin later, and you'd have in principle that look the same. And that'll be particularly important and useful as you go to higher dimensions. Okay, so then one more slide about the Gaussian. So here you can see on the left, this is the local sum of the squares of the weights. And so the blue is the initial one. And then, and as you expect, the negative weight events, they contribute just as much to the sum of the squared of the weights as the positive weight events. And so this distribution here doesn't drop in the middle, it's just the same. But if you use a neural resampler without the optimal K, So you pick like k equals 1, which is the most aggressive. You get the sum of the squares of the weights wrong. Whereas if you use the optimal value of k, it's chosen basically by construction to give you the sum of the square of the weights to be correct. And the other nice feature is on the right is the number of generated events. So if you use the neural resampler with k equals 1, you don't throw away any events. You just basically are replacing every event is the same, but now has the average weight instead of the the initial weight. But you can use the optimal value of k where you're throwing away some events. And you can see that green here is the number of generated events. And as you would expect, the region where you have many negative events, you can get away with fewer actual events that you need to keep track of to run through detector simulation, for instance, than in the regions where you have, say, the same number of positive, you have only positive events, which are in the tails. Okay, so this is a toy, but how does this work for, say, a realistic example that we care about? So here's an example where we simulated top quark pair production in excluding order using MADGRAPH and AMC NLO. And the left plot here is the PT of leading ISR jet. And I don't want to get into the details of how we simulated things, but it's we used Pythia for showering, run some jet clustering, and use final states that make it easy to figure out which jets come from the tops and which don't. And so you can ask what's the PT of the leading leading ISR jet, and has some spectrum that's shown here. And as advertised, the local cross-section is the same for all the resampling values, whatever value k you use, so that's good. And the distribution of weights is on the right. So the weights here are plus or minus 1. We've removed the overall cross-section from the weights, which you can always do because you can restore that later. And then as you might expect, the distribution of weights is broader for the optimal value of k because you have to account for the value for the events we're throwing away. But really the most important feature about this case I want to describe is that the reweighting here is not done in one dimension. It's not done for just this leading ISR jet PT. In fact, we're doing the reweighting over all of the basically object 4 vectors. And in particular, we use this neural network architecture called particle flow networks, which is based on a technique called deep sets, where we act on variable length permutation invariant objects, which is what we have in the event. So we have a variable number of jets and leptons, and we process those 4 vectors holistically.
Ben, you have only 1 minute left, sorry.
Great, yeah, I'm basically at the end, yeah. And then that allows us to look at any observable. And yeah, which is, just to stress that you can then compute anything later. So you reweight the full phase space and then decide the observable later. And just as before, we preserve the local uncertainty and we reduce the number of events. So this is kind of the same story as the Gaussian, just now with the physical observable. Okay, so that basically brings me to the end. So resampling is a model-independent method for reducing the number of events needed to run through detector simulation. You can preserve the local cross-section and the local uncertainty, which is one of the new innovations that we introduced in our paper, independent of the neural network part. And then neural networks are an effective way of parameterizing the reweighting functions to make the approach high dimensional and to give us access to the local weight. And that's it. Thank you.
Thank you very much, Ben. This was extremely interesting. If there are people who want to ask questions, please raise your hand. Otherwise, there's already a couple on the. Okay, maybe Stefano. Let's start with Stefano.
Hi, Ben. Thanks for the talk. So I have one comment and one question. The comment concerns the positive resampling, which is not your work, but still. I really can't see how this can be made general enough, because I'm afraid that the dependence on the observable is not something that you can get rid of. I mean, there's no way in which you can, at least I understand, there's no way in which you can do something which is general enough that for any observable that you may conceive, it will work in the end, right?
I think that's right. So I mean, the authors of this paper advocated that if you use one variable for reweighting, it does seem to improve the performance of other variables. Although you don't have guarantees that like you said, it's exactly correct, which is one advantage of reweighting the full phase space, and then you can later figure out what observable you want. But I agree with you. Yeah.
And the question is on neural resampling. So somewhere hidden, you must have some granularity, right? Can be effectively due to the choice of how many events you have or whatever, but somewhere the granularity must be there, because when you define your local function, local is some geometrical meaning, and therefore you have to introduce a distance, namely you effectively are dealing with some bins. Okay, so I'm wondering how first, if this is true in your opinion, and second, how this is how you can understand whether these effects are important or not.
Yeah, so this truly is unbinned in the sense that the neural network itself is it's a smooth function, and it's not there's no sense in which there's any binning or artifacts of that nature. Although it is true that the way you can kind of think about the neural network working is sort of like a nearest neighbors kind of thing, where it's sort of dynamically binning. It's like dynamically titling all phase space, and it's sort of smoothly doing some interpolation across that space. It's not actually doing that, but that's kind of like one way you can maybe think about it. So I think that artifacts from sort of binning is not really not super relevant here. In fact, neural networks are super good at interpolation, very bad at extrapolation, or not very bad, but they much worse at extrapolation, but very, very good at interpolation. And so the sort of the effective tiling is sort of given by your density of data points you started with. And so of course your precision will be best at the regions where you have lots of data points and worse elsewhere. There's no way around that. That's just by construction. But there's no like actual binning. But you can think of it kind of like dynamically binning, where like the regions of low density are the ones that'll be like kind of worse.
Okay, thanks.
Thanks, both. There's other questions. Maybe I have one question, so I'll ask it actually because it's vaguely related to what Stefano asked, which is about the physics precision, and also the essentially the fact that you have several different variables. Let's say if you go to slide 22, there's one thing which you put there. It's just okay, maybe it's a personal thing. I really think that loss functions are sometimes very much overlooked, and they're really central in the sense that okay, my approach is that you should try to define an evaluation metric and then use that as your loss function. So if your final goal is to have something which has the best physics precision, you should try to define a metric which defines your physics precision. So let's say, which essentially is the distance of your approximation through a neural network from your real distribution. The problem is that, as Stefano said, this is it's impossible to do it with one single variable, because there's so many different distributions. You might want to optimize something for a PT distribution, which is not the same for another distribution. So my question is, so first, my comment is that I'm not sure that this should be treated as a binary classifier. I don't see this as a binary classifier. I think it's much more profound than that. And I'm just wondering why you chose this cross entropy essentially, and have you considered exactly defining a different metric which is closer to physics precision, MSE, or even, I don't know, maximum mean discrepancy? I know that, for instance, there's other work by other theorists on, I think there's a paper about how to gun LHC events, and I think they use maximum mean discrepancy there. So I'm just wondering if there's some other metrics you could use.
Yeah, so in fact, you could use the mean squared error and it actually gives you the same answer. But it's really important here that you actually use a loss function which is tailored for the purpose. So I know this doesn't feel like a binary classification problem, but the magic is that if you treat it as a binary classification problem, you can interpret the neural network output as exactly the weighting function you want. And here we've used the binary cross entropy, but as I mentioned, you could actually do it with mean squared error. If you use other metrics like the mean absolute error, you get the wrong answer. You could of course modify what you do with the function at the end to get the right answer again, but it becomes much more complicated. So here it's really very powerful that you use this loss function is really tailored for this purpose. And it happens to be a binary, it happens to be the binary classifier loss function, but here you can think of it as just like a tailored loss function to do exactly what you want it to do. Now about the phase space, that's really related to what I said earlier. So one thing I kind of didn't spend too much time about is in this top court case here, we're actually reweighting everything. So we take all the 4 vectors and we apply a reweighting on that distribution, which is itself high dimensional and variable length. So you can compute any observable you like as long as it acts on those 4 vectors, and you'll get, in principle, you'll get the right answer. And so this is kind of a nice feature, as I sort of tried to gloss over here, where you reweight the full phase space and then you just have the observable afterwards. It's not the usual case where you reweight one observable and you have to check another observable. Here we reweight everything all at once.
Okay, thanks. I mean, my point was just that, let's say, when in your loss function, I think it would be nice if actually the value of L, which you get at the end, actually meant something. Like the higher it is, it means you have a physics precision which is like this. The lower it is, I mean, it's much more complicated question anyway. Sorry, let's go on. It was just to point out this. Josh, maybe. If you.
I no. Zach has his hand raised, so maybe we.
Okay, Zach, maybe.
Okay, I just wanted to go back to Stefano's second question about sort of accuracy and whether there's sort of secret accuracy issues here, which is, at the end of the day, when you're doing this, your accuracy, your network accuracy is as good as your training. So you have to have trained this thing possibly with a huge sample if you want to reweight the full phase space. And then you apply it downstream. So there's some relationship between the CPU cost of the training and the CPU benefit that you get from the use of the network, right? Have you figured out what that relationship is, how far we have to go with the training in order to win, and whether, if I care about the tails of generation and I'm going to, in the end, generate 100,000 events, then don't I end up with statistical precision issues in the tails of those anyway?
Yeah, it's an excellent question, and one I didn't spend any time talking about, but let me give 2 answers, one which you maybe care less about. So there's 2 upfront costs. One upfront cost is the training of the neural network, and the second is the generation of the events used for the training, and maybe you consider them as the same thing. But I think it's important because the upfront cost for the training of the neural network is very small. I mean, to train these networks, it doesn't, I mean, we use trained on GPUs, and it's, very, very effective. And once you have a trained neural network, you can use it forever. So that upfront cost is not so bad. But the upfront cost of the CPU generation for the, the samples you need, that can be important. And we haven't quantified it. So it's true that the neural network here is an approximation to the actual weighting function. So this magic function that we need, that's stated here, numbers 1 and 2, these are approximations. And if you knew the actual, W functions here, it would be exact. And the neural networks are an approximation to that. And it is true that, with the finite sample, finite, flexible neural network, you will not learn exactly those functions. And that's something which is a little bit tricky that is definitely worth thinking about more. And I think from the point of view of uncertainty quantification, it's something we have to think deeply about, not just for this problem, but in general. Whenever you want to use a neural network to interpret the output itself as a meaningful function, in this case, a ratio of these 2 weight functions, then you'll have this problem. Okay, thanks. We are late, but I think we can maybe take another question or 2. Maybe TJ, I've seen that you've written another question.
Hi, thanks. Interesting talk, Ben. So my question was related to the the statistical uncertainty, and in a sense, the possibility of fluctuations in your generated events after you've done the network reweighting. So I'm not sure which is the best slide, but one of the ones where you show the number of generated events with the optimal K or the weights. And what I'm observing is that your optimal K indeed you reduce the number of events that you have to generate, but then you do so by producing weights which are greater than 1, which is something I think we've tried to avoid frequently in MC campaigns, precisely because this leads to larger fluctuations in your sample generation. So can you maybe comment a little bit on how you see that affecting, say, your choices in how you want to configure this network?
Yeah, so the weights bigger than 1 here are actually essential. So if you want to match the cross section, any value of k is fine. But if you want to match the uncertainty, you have to have the weights bigger than 1 in some places. And it's not a problem. And the reason it exists is because you need, locally, if you're going to throw away 5 events, you need to make the weight 5 times bigger, right? And so it's true that relative to the, to the one where you have, let's say you use less resampling, you'll have bigger fluctuations, but those bigger fluctuations are actually the right fluctuations. And so I think this is shown very nicely on the slide 25 I'm showing here on the left plot. So the orange is if you use, you set all the local weights to be the same, so you don't throw away any events. And you see that you underestimate the uncertainty locally compared to the right answer. The right answer has a bigger uncertainty, larger fluctuations. And so it's really important actually that you multiply the weight by some bigger value, and you'll get exactly the right fluctuations that should be representative of your sample.
Okay, thanks. I didn't quite follow it the first time you said it, but now it's clear.
Great.
I can't raise my hand because I'm a co-host. Maybe if I could just really quickly to cement my understanding. So am I reading this right in the sense that by generating less events with the sort of larger weight spread, you get back the original uncertainty, but the point is that then by generating the same number of events, you get a smaller statistical uncertainty? Is that
right? Yeah. That's exactly right. I think the way to think about it is imagine locally you have a bunch of positive weights and a bunch of negative weights in the same bin. So really your uncertainty, if you set all the weights to be the average, then there's way less spread, right? You just eliminated a source of variance, the spread in the weights. But you really want that spread in the weights because it's important, it's physical. And so when you throw away events, you want to amplify their weight in order to get the right fluctuations.
Okay, thanks.
Ben, does this apply or take into account the possibility of rejecting events either by cuts or by accident? One of your jobs in the queue may fail, and then you lose a chunk of events. And then if you have a large variation in the weights, I mean that could impact the actual accuracy, right, at the end.
Right. So if your job loss is random, has nothing to do with it, doesn't depend on phase space, then it won't matter. But yeah, indeed, if it depends on phase space, if you're for some reason, your events with more jets or something, they crash more often, then it will be a problem. It's of course a problem with the standard generation also, right? You'll get the wrong answer if you in the standard way. Just like that, you'll get the wrong answer here also, but I guess it's more amplified because the whole point of you're using less events, so each event needs to represent more variation than a single event does.
Yeah.
Yeah, but it's the usual problem, right? If as long as if it's random, it doesn't matter. But yeah, I agree with you. This is yeah, that's the trade-off. Each event now carries more meaning.
Okay, thanks. This was very interesting discussion with a lot of people contributing. Josh, I see that you still have another question, or you want to skip it? And
I think we probably have to move on because we're already 10 minutes late.
Okay, so so let me thank again all the speakers. Ben, this was very interesting. Stefano as well. Thanks, Josh, for the introduction. So we are 10 minutes late, but I think we can still have a small break of 10 minutes. So we reconvene at 5:30 for the second part of this session. Thank you, and talk to you in 10 minutes then.